Hello, this is Gabriel Tijerina. This is my ENTC 689 final project over Disney's autonomous trackless ride vehicle. So as an introduction, here's why I chose this project and what exactly this means. A autonomous trackless ride vehicle, obviously a ride vehicle. It's a vehicle that carries passengers through one of Disney's rides. On the left picture there, you can see this is what a lot of rides look like, and this is how they used to be built. There's a track, very obviously, on the floor. Kind of ruins the immersion of, the whole Disney World thing, and also it just gets in the way of, if something happens, if something goes wrong, someone spills anything, you gotta stop down the entire ride because every single vehicle goes to that same track. On the right side, here's a new trackless ride. Cleanup is a lot easier. You can't see the physical track, so you kind of don't know exactly where you're going to go. Sure, there's tire marks, but that's easily, they can go in and clean it at the end of every day, or every few hours actually. Um, so on the bottom right, that's one of the newer Disney rides. Have that same picture again because let's go ahead and analyze it. Flat floor, better for cleaning up, like I said. There's no railings or padding on the walls. Obviously, if there's a track, vehicle isn't going to go off the track. But here, there needs to be some sort of really good control system so that it doesn't just go ramming into the nice decorations. Oh, can I turn on my laser pointer? Yeah, there we go. You don't want to run into any of this stuff because I'm sure they don't have just big decorations like this just lying around as backups. Also, this kind of structure, it's very awkwardly shaped, so they're probably not using some sort of just basic photo sensor because of all these jagged corners and stuff that would make the vehicle be very jittery. So how are they doing that in such a tight space? And also in this picture, there's actually it's a screenshot from a video. There's actually no exit to this room. The exit is the same as the entrance. So that brings up more questions over how exactly is this vehicle built. So assumptions have to be made. I mean, as Disney, they're not just going to spoil all of their secrets. So I've decided to assume that these vehicles use a holonomic drive chassis. You see a picture of it here on the left. That just means that there are four Omni wheels, pointed inwards at 45-degree angles. This allows this vehicle to move in any direction, forward, left, right, any 360-degree direction, while also being able to rotate about its center, about its origin. So I started my research there. Most of the research for this type of chassis ended up being in like code, because there's not a lot of, I've never seen any other vehicle carrying passengers with this type of drive base. But mostly, as you can see here, is mostly used for robots. So there's been a lot of code to power these four motors. That's where the majority of my answers were really. At first I wanted to see how I could control a DC motor. So boom, I just looked it up. I found these equations. That's nice and all, but then taking a further look at them, I'm trying to control motors that are attached to a vehicle. What parameters do I really want to control? The velocity or the position or acceleration? Looking at these equations, it has nothing to do with a vehicle. It's just for DC motors. So do I want to have four separate control systems for each motor and then somehow combine all that to make another control system for the vehicle overall? These are the kind of things I had to ask myself from the very beginning. So I decided, I'm still in the research phase. Let's look at the dynamics for a car. The holonomic drive there's no cars with that kind of drive, but this gives me a good idea. This is a free body diagram of a car. Just very obvious forces driving the car. And then there's also resistance like wind. Wind is pretty negligible. These Disney trackless ride vehicles are not outdoors. There's no wind. It's AC, but that's negligible. And they're not even traveling at very fast speeds. They have to travel very slow. They don't have doors. They have no kind of, I guess you could just step right out, but you might get kicked out of the park, which no one wants to do. But so wind is negligible, but this did bring up other forces to keep in mind, like friction and inertia for sure, because on these rides, it's like a thrill ride. You're constantly being shoved left and right. So here we go. I just started coming up with something. The code for the holonomic chassis wasn't super useful. So I had to, on the right here, you can see this geometry, trigonometry work that I did to derive these 4 equations. It's the angular velocity of each wheel. The FL stands for front left, back left, front right, back right, that kind of thing. Here's the velocity of the vehicle, this linear velocity. The radius of a wheel times the cosine of 45 degrees plus the kind of like the heading angle of the vehicle. But it's not really heading angle. It's the angle from a global. It's in the global coordinate system, the angle in the global coordinate system. So no matter which way the vehicle is facing, right? And then I have to convert that from degrees to radians. So these equations may be right, but from here I got stuck again because I don't know. Still, I wasn't quite sure what am I controlling and how am I controlling it. Basically, I knew that I had to come up with dynamics. Proper dynamics equations are differential equations, right? So I came up with these equations, these 2, velocity of the vehicle in the x direction and the velocity of the vehicle in the y direction. These are the components. And I also included the terms on the right there. That's for friction or inertia, anything. B is just basically the coefficient of friction. Include the losses. Yep. Okay. So now that I have the velocities, I know that I can integrate those velocities to get the position. So therefore, the position of the vehicle is the thing that's being controlled. And then I would have to loop that feedback back to adjust the vehicle velocity. So this is the entire Simulink. You can't see it, that's fine. I just want to show this is the entire thing. There's 2 scenarios that I wanted to demonstrate or simulate. One is a vehicle traveling in a straight line. I thought this would be easier. And then the second one that I had in mind was the vehicle traveling in a circular path. Turns out these are the exact same block diagrams. The only thing that's changing is the input. Here, this is the top half. This is the ideal section. The 4 equations for the velocities, they're seen in this red box. From before, it's just the input angle plus 45 degrees. Convert those degrees to radians. Take the cosine of that and then multiply that by, it's not technically in the red box, but the velocity of the vehicle divided by the radius of a wheel, not the radius of the vehicle. So that equals the angular velocity of each of the 4 wheels. Now in this red box, we have the spin parameter. It's simply being added to the angular velocity of the wheels. It turns out that if you want to spin, say counterclockwise, you just add. That's just the same angular velocity added to each wheel. And if you wanted to spin clockwise, then it's the same angular velocity subtracted from each wheel. And the equations will work it out. Here we have, in this red box, this is the last 2 equations that I showed, the velocity of the vehicle in the x direction and the velocity of the vehicle in the y direction. Nothing fancy going on here, but that's where the actual system comes into play. So here is part of the actual system. It was too big, but the 4 angular velocity equations are the same, exact same thing. So I kind of cut those off. All that's important is the velocity of the vehicle in the x and y directions. So you can see the velocities are in the x direction and the velocity in the y direction. They're integrated. That gives a position. Of course, the other term is added or subtracted technically on. And then the error of the positions are calculated from the ideal position of the vehicle. And then that is used as feedback to to adjust the velocity of the vehicle in the X and Y directions. And from there, that new adjusted velocity in the X direction and the Y direction, they're put back together, just Pythagorean theorem. And that gives the total linear velocity of the vehicle. It's a lot of words. And then that new calculated velocity of the vehicle is then used to calculate the new angular velocity of all the wheels, and then the linear velocity of all the wheels, and then the percent duty cycle. So the percent duty cycle is really like the useful information that's being outputted. It's not the only output, but that's the thing that's actually controlling the vehicle, right? So you need to know that. Oh, I just have the red box showing that's where the error is being calculated, and then that's where the linear velocity is being calculated from the X and Y components. So that was my simulating construction. Here are the results. When I say first and foremost, I was a little late to say this in the report, but here's a convention for the angle, the heading angle, right? So if the angle is 0 degrees, if the input angle is 0 degrees, that means that the vehicle is traveling straight forward. And then say 1 degree, 2 degrees, 3 degrees, it moves in a counterclockwise direction. So 45 degree input angle is this line shown here, straight through that front left wheel. And that's what I have on the plot on the right here. For this simulation, the straight line, it's 45 degrees. So looking at the top left plot, this shows the angular velocity of all 4 wheels, but you can see in the legend there's 4 wheels, but there's only 2 lines. Why is that? The wheels that are opposite from each other, let me go back. Can I go back? Yes, the 2 wheels that are opposite from each other, so the front left wheel and the back right wheel, for example, those 2 speeds are always the same. And then the same thing for the front right wheel and the back left wheel. Those 2 speeds are always the same. So that's why top left plot, there's only 2 lines, because the back left and the front right wheels, those plots, they overlap with each other. So 45 degrees, why is this 0? Why is the front left wheel and the back right wheel angular velocities 0? Because, going back, lots of back and forward, there's no reason for the front left and the back right wheels to spin at all. You can see the back left and the front right, those are the only ones doing all the work. It's moving in a diagonal direction. The same amount left, same amount up or forward. There's no reason for the front left wheel to do anything. And then the second plot is the linear velocity. So you can see 0 again and 10. The input velocity for this simulation is actually 10 meters per second. So I calculated the angular velocity and then went back to linear velocity, and it's still 10, so that's correct. And then on the right, the plot, that shows just a percent duty cycle of the 4 wheels. That's not, I just came up with any parameters because, again, I don't know what kind of motors they're using. So this just gives a representation, 0 and then something. There is, at time 20 seconds, there is a shift upwards. That's the spin. So the spin, I didn't include that until t equals 20 seconds. At 20 seconds, the vehicle is actually spinning counterclockwise with I think an angular velocity of 2 radians per second. So that's why it jumps up by about 2. And that's all 4 wheels. And then on the bottom, those show the same plots, but instead of the ideal system, it's the real system. So on the bottom left plot here, you can see, again, 2 of the wheels are at 0, but the other 2, they start at 25. That's what they're supposed to be. Those are the initial conditions that I inputted. But then, like into the integration block. But then, as time goes on, very quickly, they're adjusted. It increases. Why is that? Because there's losses in the system. So the vehicle isn't actually moving at 25, or let's look at the second plot, the linear velocity, the vehicle isn't actually moving at 10 meters per second because of the losses. So because of that, it has to compensate and increase its percent duty cycle to the motors, for example. And now it thinks it's traveling at about 12 to 13, excuse me, about 12 and a half meters per second, but it's not. That's just what it thinks it's moving at. Okay. Here's some more plots on the top left that shows the velocity of the vehicle in the X and Y directions. It's moving diagonally, the same amount left, same amount up, so that's why both are the same. Notice how at time equals 20 seconds, there's no change. Why is that? Because the vehicle is, all four wheels have increased by the same percent duty cycle. So it's spinning, but it's not moving tangentially. It's just rotating about its origin. So that's why there's no difference there. On the bottom, the target, it thinks it's at, what is that, 7? It's at 7, but because of the losses, it has to increase itself. And then the vehicle position for ideal and vehicle position for actual, those are the same. Why are they the same? Because the control system worked. It adjusted the percent duty cycle and the angular velocity, linear velocity, all that, it adjusted all of that properly so that the vehicle position is matching the ideal circumstances of the vehicle position. That's what's being controlled here. And then the right, you don't really need to know that. I just threw that in there. It starts at 10, but the linear velocity of the vehicle actually jumps up to, 12.5 from earlier. That's what it thinks, that's its target, but of course we know it's not actually moving at that speed. Okay, here's the second simulation. This is the circular path. The only thing that changed here is instead of a step function, it's a ramp function. So the slope is 9. That's because 9 times 5, that's 45. So at 5 seconds, the input angle is 45 degrees. And at 10 seconds, it's 90 degrees. So it's easy readability that way. So you can see on the top left graph, at 0 seconds, the input angle is 0. So the vehicle is moving straight forward. That's why all four wheels are moving at the same speed. And then at 5 seconds, it's moving at a 45-degree angle. And that's from the straight line simulation from before. 2 of the wheels are moving at 0. 2 of them are moving at about 25, it looks like. At 10 seconds, it's moving at a 90-degree angle. So all four wheels are moving at the same speed, just in different directions, a little bit less than 20. At 15 seconds, the vehicle's moving at 135 degrees, so diagonally down to the left, basically. 2 of the wheels are at 0. Let's see, that would be the back left and the front right. And then the other 2 wheels are moving at its maximum throughout the entire simulation because they're responsible for driving the vehicle all the way. And at 20 seconds, the vehicle's moving just backwards. So that's why all the wheel velocities are the same. Again, also at time equals 20 seconds, that's when I inputted the spin. So that's why there's a slight, increase in velocity. And then again on the bottom, it shows the actual, or the target, angular, linear velocities and percent duty cycle. You can see it's very similar. The only difference is at the very beginning, there's a slope. It acts a little bit weird. That's because it's adjusting itself in that 1 to 2 seconds. And then again, I have the ideal vehicle velocity in the X and Y direction, and then the target. Again, once again, there's a slight weird bit at the beginning, and it's calculating. It's adjusting itself. And then the 2 vehicle position plots, they're exactly the same because the control system worked. So lessons learned. I'm kind of smart. I viewed this project as kind of a hard homework assignment. I wanted to come up with everything. I wanted to figure out everything. That's why the literature review kind of lacked, or it was a little bit short. It wasn't very in-depth because I wanted to try and do everything all by myself. And I did, I think. Well, I did do all of this by myself. Even if it wasn't like super fancy, I didn't want to just copy off of some PhD students or some company out there. I don't want to just copy their work. Whatever I did it entirely myself. And I'm kind of happy with that. The other things are more technical things, like in terms of control systems. It's a lot easier to solve control systems when like it's presented, then the dynamics are given to me and the states are given to me. I didn't really have to think about what anything means. I just had to do the math, right? You can do math without knowing what any of the variables mean. So, in conclusion, I made an observer control system for one of Disney's autonomous trackless ride vehicles. I ended up controlling the position of the vehicle and using that feedback to adjust the velocity of the vehicle. And it worked out. So, thank you.